Hello. In this video, I'm going to bring you to a journey of establishing central limit theorem. We have 2100 number here. This is our population. We calculate the population mean, standard deviation, and proportion. But now, in this case, we suppose we pretend we don't know the all of this. We want to use sampling to figure out or to estimate the parameters of population. The method here is we are going to get 1,000 simple random samples from the population. The sample size is the same, 30. And then draw the information from these 1,000 samples. This is our 1,000 samples. Let's come over here. We calculate the mean of 1,000 samples, the standard deviation, and the proportion of these 1,000 samples. And these red values is the average of this column of data. This column of data is referred as sampling distribution of the means. And this value is the mean. The mean, you look at the formula, the mean of this column of data. This column of data is referred as sampling distribution of standard deviation. This value is the mean average, the mean of this column of data. This column of data is referred as sampling distribution of proportion. Anyway, these three columns of data is sampling distribution of our statistics respectively. Let's compare these values to the population parameters respectively. Oh, this value is very close to the population mean. And this value is very close to the population standard deviation. And this value is very close to the population proportion. This information gives us, we can use some samples to represent or to estimate the population parameter. Theoretically, if we list all the possible samples here and calculate every samples, maybe 1 million, 10 million samples, mean, standard deviation, and proportion, and then we calculate every mean of these three columns. So this value shall be exactly equal to the population mean. This value shall be exactly equal to population standard deviation, and this value shall be exactly equal to the population proportion. But here we only have 1,000 samples. That is why these values are slightly different from these three values, but they are very close. Anyway, our conclusion for this information is we can use some samples to estimate the population parameters, or we can use some samples to estimate the true. Let's move to step 2, dive deeper. How about we only can use one sample to represent the population or to estimate population? For example, sample 1. If the content of this number of this population is the weight of a can of tablet pay reliever, and one of the criteria for production monitoring is the proportion of the tablets fall in this target range shall be over 90%. And if we happen to pick this sample, we can make the same conclusion as we have the whole population. This is a good sample. But if we happen to pick this sample, we are going to make an error because the true population proportion is below to 90%. The production is bad, need to be halted to make adjustments. But we pick this sample to represent the population. We will conclude that the production is good. Keep going. Our conclusion of this information is most of times we can use a sample to estimate or to represent a population, but sometimes we make errors by use just one sample. Let's move to step 3 and visualize these 3 columns of data. We have 3 graphs. They look different, but they have the common graphs. All the graphs looks bell-shaped. That means sampling distribution of our statistics follow normal distribution. That is the central limit theorem comes from normal distribution. The true is in the center. The mean is in the center. Here we just express as the true is in the center. The spread is limit, and the empirical rule applies. Let's just focus on 95% and focus on the means, sampling distribution of the means. 95% of the data points, we have 1,000 data points. 95% of the data points fall within 2 standard deviation of the mean. And we want to figure out what is the mean of this graph. What is the mean of what is the standard deviation of this graph? Because this graph, this bell-shaped graph comes from this column of data. Let's go back to this column of data and calculate the mean of this column of data. We got this value. And then we calculate the standard deviation of this column of data. We got this value. And we want to figure out these values. Do these two values have relationship with the population mean and standard deviation? Obviously, these two values is very close, almost equal. But this value is very different from the population standard deviation. Do they have relationship? Yes. If we use this formula, the population standard deviation divides by sample size. Here the sample size is 30. We got this value. We compare these two. They are very close. Theoretically, if we get all the possible samples and list here and calculate the mean of every samples, all the possible samples, and then we got this column very long, maybe 1 million, 10 million, every sample's mean, and then we calculate the mean of this column and the standard deviation of this column. Theoretically, this value will be exactly equal to population mean. Theoretically, this value will be exactly equal to the population standard deviation. But right now we only have 1,000 samples. That is why these two values are slightly different. Theoretically, this value shall be equal to population standard deviation divide by square root of sample size. And now we qualify the these two values and the relationship with the population mean and standard deviation. This is the central limit theorem for sample means. You just read through it. Also, if you go to proportion, this column of data, you calculate the mean of this column and the standard deviation of this column data. You can figure out the relationship of these two values with the population mean standard deviation and population proportion. I think you can figure out and read through this. Anyway, in real life, we usually need to address the population. We don't know the population means standard deviation and proportion. And we only can draw one sample, randomly draw one sample from the population. And if the sample size is big enough, means at least 30, we can use the sample standard deviation to replace the population standard deviation and use the sample proportion to replace the population proportion. These two values, I just use sample one's standard deviation and proportion to substitute this formula to calculate this formula. And I got these two values. They are very close, acceptable close. That is the foundation of inferential statistics. You can play around here to establish more about central limit theorem. Thank you.